Welcome to Castle on Ankara. It's a snowy afternoon and we're going to talk some science. Today's topic is going to be a very underappreciated tool in the world of commercial growing, and that's the EC meter. These science talks are not geared towards growers of any particular crop, but they're geared to people who grow any crop, food production, floriculture, high value, medicinal, because the science is all virtually the same with just some slight variations from crop to crop. So all of the science that we talk about here in this series is science for everyone. I'm a science consultant to the controlled environment agricultural world, both for food crops, flora crops, and high-value medicinal crops. I do science evaluations and advising for maximum and optimal production with the lowest input cost for the crop production. So for those of you who have a science background, we're going to cover just a few things that may be old hat for you. For those of you who do not have a science background, do not worry. We're not going to get too deep in the weeds, but the importance of the science that we'll talk about today and in subsequent videos is that your ability to understand basic concepts of science in the agricultural world will help you maximize your productivity, maximize the quality of whatever crop you're growing, and keep your input costs, cost of production at a minimum so that your business can be successful. I also am a commercial grower. I grow vegetable and flower seedlings for a couple of different retailers. We probably grow 30,000 seedlings every spring in a greenhouse operation that is an outdoor operation based on super insulated chambers within the greenhouse and automated light application within the chambers. We have no furnaces. So we run high-tech operation, and we run it because it allows us to produce far more product, higher quality, less labor input, and we don't care what the weather outside is because we can maintain optimal conditions within the growing chambers. So let's start by first looking at a simple graphic. When we look at any plant, whether it's outside in a conventional field application or inside in a container, we basically have above the soil line, below the soil line. Above the soil line, what we're trying to control are things like CO2 concentrations, the light energy in the form of photons that gets delivered to the plant. The plant can take in some levels of oxygen above ground. What we're interested in today is below ground. The plant can also take up some oxygen here, carbon, takes up water. This is what we're interested in today, are the nutrients that plant needs to grow and to produce whatever crop we're specifying. We have the macronutrients, the nitrogen, phosphorus, potassium, secondary nutrients, calcium, magnesium, the micros, the borons, the molybdenums. So we have a number of different elements here that need to be delivered to the plant for that plant to reach its optimal growth and productivity potential. So when we start talking about nutrients, if I ask most of you to give me a list of nutrients that we need to deliver to the plant so that the plant can successfully grow and produce, you would probably be able to name most of these on the list. Nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, chlorine, iron, zinc, manganese, boron, copper, molybdenum. These are the nutrients that we know the plant needs. And when we talk about these nutrients, if we're familiar with the periodic table from your days in high school chemistry and physics, we know that each element is associated with a letter that designates that element on the table. So nitrogen is N, phosphorus is P, potassium K, calcium Ca, magnesium Mg, and so forth. These are all in their elemental form. They're not combined with anything, and they don't have an electrical charge. They're neutral, stable in their elemental form. So let's take a look, though, at what it is that we need to give to the plant in order for the plant to be able to take up these essential nutrients that it needs. Now, here is a list of the nutrients that we just looked at that the plant needs. And on the right in the red is the form that these nutrient elements need to be in for the plant to be able to take them in and use them in all of its metabolic processes. Nitrogen. Now we're no longer dealing with just N. We're dealing with NO3 negative or ammonium NH4 positive. Phosphorus, we can have H2PO4 negative. Potassium, K positive, calcium, Ca positive 2, and so forth down the line. It becomes very apparent that this list of elements and elemental form of the nutrients is not the same as this list of the form of these elements that are necessary for the plant to be able to take that element up. And if you look at every one of these elements in the form that the plants need in able to take them up, you'll notice that they all are associated with either a plus or a minus charge. Some of them may be a single minus, others may have a plus or minus 1 or 2 or 3 or even 4, but they all have a plus or a minus charge. The plant cannot take up its essential elements in this form. They need to be in this positive or negative charged form, which from your chemistry days you know are ions, or this is the ionic form. An ion is the single element with a positive or negative charge. Something like the nitrate, that is an N combined with something else, an oxygen or a hydrogen with a charge, is what we call a polyatomic ion. It's just a couple of elements hooked together, but that group, that molecule, still has a positive or a negative charge. So we have ions or polyatomic ions, but the important thing to remember is every one of these nutrients to be taken up by the plant needs to be in some ionic form. So the first very simple rule and principle of what we're going to be talking about today: nutrients must be in the form of ions or ionic compounds to be taken up by plants. They must be in that positive or negative charged format. And an ion is an atom or a molecule that has a net electrical charge. Remember, we saw things like nitrogen in a NO3 negative, that's a polyatomic or an ionic compound. So they must be in an ionic form, and an ion is an atom or molecule that has a positive or a negative charge. So let's look at this in an everyday useful to you format. what has all this ionic compound and ions got to do with us as growers? To answer that, we're going to look at probably the ionic compound that is most familiar to you and the simplest one we can talk about that will show you what an ionic compound is, how it is formed, and how we use it in our grow process. So the most common ionic compound that you're going to be familiar with is simple table salt. Sodium and chlorine. Simple table salt. And you're all familiar, this is the solid state of sodium chloride. Simple table salt. Another thing about ionic compounds is that they are soluble. When you put them into solution, into say water, which we use in our daily grow process, those ions, the two that are held together, separate and become free within that solution. So an ionic compound is soluble. The simplest soluble ionic compound that you're familiar with that we'll talk about is table salt. However, the most important ionic compound to you is the fertilizer that you will be using in your grow operation. Ionic compound, ionic compound. If we can understand this one, we can understand this one and have a better idea of how to use it and how to control it within our grow operation. So let's take a little look at this simplest of ionic compounds, and that's table salt, sodium chloride. We're going to bring you back for a moment to your high school chemistry and physics days and take you to the periodic table. We're not going to spend time discussing the periodic table. You're all familiar with it, all of the elements laid out in a very scientifically based format that tells us a lot about the atomic structure and the reactability of different compounds. So let's look at the two involved in this simplest ionic compound, sodium and chlorine. A sodium atom on the periodic table, we look and it has an atomic number 11. That means there's 11 protons, those positively charged particles in the nucleus, which means because it's neutral, there are also 11 electrons orbiting that nucleus. Chlorine, on the other hand, has an atomic number of 17, which means it has 17 protons in the nucleus, and it has 17 electrons orbiting around that nucleus. In a simplistic definition, electrons will orbit the nucleus in what we call different shells, different distances out. So you can think of the nucleus, and then the first shell is kind of a clear, think of a clear sphere around that nucleus. That's the first shell. Out a little way from that is the surface of a second clear shell. That's the second orbital layer for the electrons. The third is a little bit further out. So we have different electron shells in different configurations. In general, and again, don't you quantum physicists, we're going with thumbnail explanations here. In general, we can say that in that first outer shell from the nucleus, there are 2 electrons in orbit. We hop out to the next shell out, and there are 8 in that second shell. We hop to the next shell out, and there are 8 in that shell. And we can actually go out to many more shells, but we're not going to do that right at the moment. There's a rule in physics called the octet rule. And that says that whatever the inner configuration of electrons, that atom would prefer to have the outer shell, that outer shell, it would prefer to have all 8 spots filled with electrons. The octet rule. It would prefer to be full on the outer shell to have a more stable configuration. If we look at sodium, that's a atomic number of 11 protons, and then 2 in the first shell, 2 electrons, 8 in the second shell, we're up to 10. If this outer shell were full, we'd add another 8, we'd have 18. But there's only 1 in the outer shell. So we've got 2, 8, and 1 in the outer shell. So the sodium is basically, it's stable, but it's not as happy as it would like to be. It would like to have the outer shell, whatever layer that is, it would like to have it full. Chlorine, on the other hand, with 17, we have 2 in the first shell, 8 in the second, we're up to 10. Then it has 7 in the outer shell. It's almost full. So it's pretty happy, but it's like, you know, we could be a little happier if we had 1 extra electron. So you can probably see what's going to happen here. If we put these things in the right conditions, say in solution, where they're floating around and they're free to move, they will stay apart from each other until we do something like take some seawater, put it on a hot surface, and you watch the water evaporate. All of a sudden you see white crystals forming, which is the table salt. That's the table salt configuration that we know, the solid form. So if we have a solid form and put it into water, the atoms are dissociating. When they come together to make this product, or to make this product, they involve some type of a process where we take the ions in either a gasified or a liquid configuration, put them through a process where they will come close together, interact, and then a very interesting thing happens. When we do sodium and chlorine and get them in the right condition, sodium will say, you know, I'd like to get rid of this outer electron. Chlorines, you know, I got a spot for 1 extra electron. So this 1 extra electron, this electron from the sodium, hops over and fills the shell of the chlorine. So now it has a full outer shell, and now we've gotten rid of this excess one, this outer one on the sodium. So now its outer shell is full. So they're both happier in the sense that they feel more stable. However, if we have an atomic number of 11 here, we've still got 11 protons, but now because we've lost 1 electron, we have 10 electrons. So we have now lost 1 electron, so there are more protons than electrons, so we have a net positive charge. We have Na positive because there's 11 protons and 10 electrons. Conversely, with chlorine, now it's picked up that extra one, it feels stable, but now it's got 18 electrons and 17 protons. So the electrons are negative, we got 1 more than the protons, so it now has a net negative charge. And we know it happens in nature when you have oppositely charged particles. They want to attract each other. So we have the sodium and the chlorine come together, and they get bonded by what we call an ionic bond. They don't share electrons back and forth like with a covalent bond. It's more of an electrostatic attraction that binds them and forms the crystalline form of the table salt or the ionic compounds that are in your bag of nutrients. So understanding this very simple process of what an ionic compound is, and again, when we take this and put it into the solution, these two move apart now in their positive and negative configuration, and we now have ions in our solution, but they're ions that are in the form that we saw that are now available to the plant. So ionic compounds, ionic compound, ionic compound. When you look at the ingredients in your nutrient bag, you'll notice it doesn't say nitrogen, N, calcium, Ca. It'll be like ammonium nitrate or magnesium sulfate. Ionic compounds that when they go into solution, they break apart, and you have now the ions of the two elements. So now we have a basic understanding of what an ionic compound is, how they're formed, how they go into solution, and now when they are free in our nutrient solution, they are available in this positive or negatively charged ionic form that the plant can now use. Positive ions are called cations. Negative ions are called anions. So when we get a beaker or your watering can and we've put sodium chloride into it, we have the water molecules, the H2O, and we have the Na positives floating around, and we have the Cl negatives in there too. So now we have an ionic solution. This is a word that you've probably seen before, and as we move forward with some of these science talks, you'll see again. This is a term that you probably, a term that's probably caused you a little bit of consternation when you're reading about plant science, and that's the cation exchange capacity. It has to do with your grow medium or your soil. Soil or grow mediums are made up of particles, solid material. In a sandy soil, a lot of it can just be sand particles and mineral particles. In something like a peat moss or a cocoa, the background, most of it is an organic fiber, but they're solid structures that form the physical nature of the soil. All of those solid components, like the fibers in cocoa, they themselves have electrical charges for a number of different reasons. We don't have to go into it, but some particles have higher negative charges. The particles in soils and grow mediums are normally negative. A sandy soil, like we said, made up of primarily sand particles, has a very low ion or a cation exchange rate. It means that the particles of sand don't have much of a negative charge to them. And what the positive and negative charge does, obviously when we put in positively charged ions that are in your ionic solution, your ionic compound, things like calcium, magnesium, potassium, they're all positively charged ions. You put them into soil. If you have a negatively charged solid bit of soil, whether it's a peat moss particle or cocoa or sand, the strength of the negative charge on that particle is going to greatly affect how these positively charged ionic compounds react in the soil. Say out in a field, you put your fertilizer down and you've got a very sandy soil with a very low cation exchange capability. It means the negative charge on the particles is low. These positive nutrients that you put in the form of ions in a high cation exchange capacity mix, those positives will be attracted to the negative particles in the soil and actually be held by that particle and released as the plant roots come in contact and actually pull them away. In a low cation exchange capacity soil, nothing will really hold those positive cations, so when it rains or you fertigate, they wash through. So the benefits of a higher cation exchange capacity soil is that it will hold nutrients in the soil better, and you won't lose as many nutrients through either fertigation or general watering. So cation exchange capacity, again, has to do with this very simple chemistry that we're talking in the soil. Another critical factor when we start talking these ion and ionic reactions, in most of the reactions, the biological and biochemical reactions that happen in a plant, some form of electron transfer back and forth between compounds is what's happening. That's the whole ATP photosynthesis process, is transfer of electrons, which are basically the energy packets. So this ion exchange is critical to understand in plant biochemistry, and we'll talk about it. We'll talk about it a lot more again in subsequent videos. And the last phrase that you've probably come across in your readings on plant biology are oxidation and reduction reactions, which again are a critical and ubiquitous reaction that happens within the biochemistry of the plant. And again, this oxidation reduction merely refers to the losing or gaining of electrons. Oxidation is when a compound loses an electron to some other compound. Reduction is when a molecule or a compound gains an electron. So just having a basic understanding of this is going to open a lot of doors for you as we look at optimal growth down the road and talk more about things like nutrients, how they get into plants, how the plant uses them, how you can control them better to work in conjunction with the plant. Let's take a second and just do a really quick review. We know about ionic compounds now. We know that the plant needs to have nutrients that you put in be in the form of ions and ionic compounds. We know that down the road this whole concept of ions and ionic compounds and reduction, oxidation, redox reactions are all going to center around exactly these simple things we're talking about. And again, you won't need to go out and get a PhD in chemistry to understand as we talk about these. We're going to put them in a very simple format. So we understand the ions now. Let's look at how this relates to us as growers, and how does it relate to this topic of the day being EC meters. Another basic principle of ionic compounds and ions in solution, making ionic solutions, is that because those ions have positive and negative charges, they will conduct electricity. Electricity is basically just the movement of any charge. So if ions are moving in a direction, that is an electrical current. So when we have a beaker or your watering can and we put our table salt in, we'll stick with table salt at the moment just because it's the simplest one to understand. We have our beaker, we have our water, we've put some table salt in here, so we have the water molecules, the H2O, then we have the positively charged sodium ions, the negatively charged chlorine ions. And we know that ions and ionic solutions will conduct electricity, will conduct an electric current. So an EC meter is basically just a black box with a little computer in it and a battery. The probe on the end of an EC meter really just has two elements separated by a tiny space between them that we then place in this solution. The red and the blue here just represent the electrodes in the EC meter. I've just got them far apart so that you can visualize it better, but they're actually very, very close together. So with the EC meter, we turn the EC meter on, and what it does is it just sends a tiny electrical charge into the probe, which will then send a tiny electrical current into the solution. If there are no ions in the solution, there's nothing to carry the current, and in theory the EC would read 0 because that there would be no conductivity, because there would be no movement of ions. But as we add an ionic compound and it dissociates into its ions, we put a current in. The two elements in the probe, one is positive and one is negative. The positive one is called the anode. You'd think, well, wait, if it's positive, I thought an anion was negative. The reason it's called anode is because the positive attracts anions. Anions go to an anode. The cathode is negatively charged, and it attracts the positively charged cations. So it's a cathode. So we induce a little current, and the concentration of the ions in the solution will determine how efficiently and effectively that current is transmitted across the electrodes. The computer down here just does some very basic calculations that equate to the higher the number of ions in this ionic solution, the higher the conductivity, and the higher the number will read. That number is in a unit we call, or the meter is called an EC meter, which stands for electrical conductivity. It's measuring the conductivity potential across the two electrodes. So we know how an EC meter works now. We know the electrics, we know the physics. Our job now is to make sure that we use this tool correctly when we start delivering nutrients to the plant. One of the important things to know about EC meters is they will not tell us what the relative concentration of the individual elements within that nutrient solution are. It won't tell us what the concentration of nitrogen is, or the concentration of phosphorus, or the concentration of potassium. It gives us a total score for the conductivity in there. That brings up the very important point that when you decide to use a soluble nutrient, a soluble ionic compound to feed your plants, that you're putting trust in that company that, number one, it's science-based, it's data-driven, and that when they tell you on their feed schedule that at a certain stage in the growth of that plant, you should be feeding an EC level of, say, 1.8 on the input, that when you make up that 1.8, that the nitrogen is in the proper form, all the other elements are in the proper form, but that also all of the individual elements in that nutrient mix are in the proper ratios to each other, that the nitrogen is in a proper ratio to the phosphorus, is in a proper ratio to the potassium, is in a proper ratio to the calcium. Because nutrient solutions that are not in the proper ratio can be very troublesome for your plants. Nutrients work either antagonistically or protagonistically with each other. Too much of one compared to another that would like a certain ratio can cause uptake issues. We can cause changes in pH. We can disrupt the mechanics of the soil. We can disrupt things like the osmotic potential across the root cell walls. So the science that goes into a good commercial ionic compound is very precise and essential for you. Something as simple as a company that decides to make a nutrient and they don't really follow the science. We'll tell you, we have all the iron that your plant needs, and we know iron is essential for proper growth. But iron can come in a number of different ionic formats. It can come in Fe2 positive or Fe3 positive ferrics or ferrous. The plant can use one, and it really can't use the other. So it may be cheaper to put the form that the plant can't use. And if you don't know this, you can be giving your plant what you think is a complete and well-balanced nutrient, but it ends up causing iron deficiency problems, and your yield and your quality will go down commensurately. So using the EC meter is going to tell you the correct concentration of nutrient you're giving, but we're making the assumption that you're using a nutrient that was developed according to science, so that when you reach that EC, it's the level and the concentration and the ratios that your plant is looking for. So let's take a real quick look at an EC meter. So this is a Hanna EC meter, widely used. This is probably like a $300 meter. It's one that I use. I can't go anywhere without EC meters. If I turn my meter on and we test a sample of RO or distilled water, I put the probe in. Now, because distilled and RO water have taken out all of the ions, we would assume we're going to have an EC of 0. There's a tiny bit of conductivity, like a 0.05 even with pure water, but in effect it's 0 because there are no ions to conduct an electrical current. So the EC meter will not read a conductivity factor, and it'll register 0. If I take a sample of my well water, and I asked you guys what you think the reading would be, some of you might say 0, but when I take a reading, I'm actually getting a reading around 0.35. The reason it's not 0 is because we're dealing with well water. Well water is coming through the ground. When water travels through the ground, it is dissolving some nutrients in the sand and in the rock that it flows through. So it's picking up things like calcium, iron, magnesium, sulfur. Those things you smell and see in your water. Those iron rings in your toilet and the calcium. Those are all ionic nutrient salts that are already on board in the water. So that if I look at a feed schedule from a company and it says, okay, on week 5 we want you to be giving an EC of 1.5, and you say, okay, you go draw a gallon of water, and it says put a teaspoon of our mix into a gallon of water, and that'll get you to an EC of 1.5. Well, they're making the assumption you're using RO or distilled water. They're not taking into consideration that your water already has a background of 0.3. I've seen them up to 0.7, 0.8. So you may take a gallon of water, put a teaspoon in and say, there, I'm at 1.5. But if we put an EC meter into the water now, we'd have that 1.5 from the mix, but that 0.7 from the background in your water. So we would actually be at a much higher level. We're going to be up around a 2.2, which may be too much for your plants at that stage. So the importance here is knowing that your background water has an EC level and how to incorporate that into your process of mixing up your nutrients. So if you've got EC meters, you should always mix your nutrient and then check when the final product is made. Don't just go by the package that says put a teaspoon in per gallon and assume that it's going to be correct. So EC meters are the tool that's going to allow you to be precise on your fertilizer application. Now, a big question that I get a lot is from people who say, well, I prefer using ppm. So let's look at that question. What is ppm? ppm is basically parts per million. It refers to a milligram per liter of a substance. And ppm are calculated using a TDS meter, a total dissolved solids meter. If I take a sample of water and I put a little bit more sodium chloride in and increase the conductivity, I take my manometer, I put it in, and I'm now reading an EC of right around 1. I ask you to take your TDS meter, put it into that water, and you're probably going to tell me most of the time that you're going to get a ppm reading of 500. Now I can take this manometer and shift scales from EC to parts per million. I'm real close to 700. You're going to look and say, wow, either this meter's off or that meter is off. Actually, they're not. ppm is calculated using a conversion factor from the EC reading. Most meters out there, most American meters, use around a 0.5 conversion or 500 conversion, where it takes they calculate the EC first, multiply that times 500. So if we're dealing with an EC of 1, multiply it by 500 conversion factor, 1 times 500, we're going to be looking at a ppm of 500. This particular meter, for a number of different reasons, uses another conversion factor that is still fairly widely used out there, which is around a 0.7 conversion factor, or 700. That takes that same EC1 reading, multiplies that times 700, so it gives me a ppm reading of 700. So if you're talking to me, you're having problems with your crop, and I ask you about the fertilizer rate and everything, and what are you using for a feed schedule, what level are you feeding at? You tell me 500, but I think in terms of a 700 ppm, we're talking different languages here now. If we start talking fertilizer rates up around 2 for an EC, which is common with a 500 meter, you're talking 1,000 with a 500 conversion. I'm talking 1,400 with a 700 conversion. It's just that we're talking different languages, and it's apt to be very confusing for both of us if we don't know which language or which dialect we're speaking. But the thing about it is that both meters calculate that EC first and then figure the ppm with a conversion factor. So if instead of talking ppm we talk EC, we're both talking the same language. My meter is going to read an EC of 1 or 2, whichever one we're talking. Yours is going to read 1 or 2. The difference comes when your computer or my computer multiplies it by a different factor. So I'm a huge advocate, and most of the grow world, the commercial grow world, advocates using EC as a language rather than ppm to avoid that translation problem. So I'm just a huge fan when we start talking EC meters, is to speak in EC language. This is just a little review of our beaker of water, or our watering can, or our nutrient reservoir. We've put the nutrients in. Now we have all of these ions and polyatomic ionic compounds floating around in the form that the plant can use in the right concentration, because we've looked at the feed schedule. We've determined what EC level we should be at. We've put our EC meter in. We've checked that the EC is right. Because we know that if these nutrient concentrations are too low, the plant is going to suffer. We're going to have a reduced yield, and we're going to have lower quality. If these levels are too high, we're going to have toxicity issues, burning of the plant, a complete reduction and potential shutting down of some or all of the biochemical reactions that the plant is trying to carry out. We also can have a great disruption of all of the mechanical and physical and chemical properties of the soil due to disruption of pH or a disruption of the osmotic potential. The water and nutrients, one of the prime ways that water and nutrients get into a plant is through osmosis, and there has to be a differential between the inside of the plant and the outside. We'll do a video on osmosis shortly so that you can understand that, because when we disrupt the osmotic potential, you can actually have plenty of nutrients and plenty of water in that grow medium. But if the osmotic potential is off, the plant actually may be dumping water back into the soil instead of taking water and nutrients in. So very critical that we use an EC meter to determine where we are in this whole process. A short review here. We need to choose a complete and balanced water-soluble nutrient. Again, it needs to have all of the elements that that plant needs in the right ionic form to be used by the plant, and it needs to be balanced. Things have to be in the right ratio to each other. Follow the feed schedule. Use your ppm. Use an EC language instead of a ppm. Again, ppm is not wrong. It's just it can give us some translation problems. Calibrate your EC meter occasionally. Test your water and make sure you check the EC after you've made your mix. Fertigate using a continuous feed protocol. All of the peer-reviewed research out there, decades of research, have shown that plants that are fertigated, fed and watered more frequently in a higher porosity mix produce higher yields and better quality. Feed schedules such as the one from Jack's and GH, most of the companies are assuming you're using a continuous feed. These EC ppm targets are for people to use a continuous feed, and that means every time you water, you feed. So we now know the first half of the EC meter equation. We have a better understanding of the chemistry and the physics of why EC meters work. We have a better understanding of how to use them as growers to assure that the nutrient that we deliver to our plants is in the right format, the right ionic format, and that it's balanced. It has all of the nutrients that that plant needs, and everything is in the proper ratio. So we're talking good quality nutrient lines. That's what you pay good quality nutrient manufacturers to do, is to make sure that you're getting all of those elements. The quality, the proper ionic forms, and the balance. And we now know how to use your EC meter. We know to talk in the language of EC rather than ppm. What we're going to do is take a break here, and we'll shortly look at part 2, and part 2 is going to show you how to use your EC meter to do what I, as a science consultant in the field, have found and advocate as being perhaps the number one procedure that can give you the greatest control over your grow and put you in a proactive format with your grow operation rather than reactive. It'll allow you to know exactly what's happening to your plants and to prevent things that most growers end up reacting to when they've already lost days or weeks of optimal growth because they couldn't anticipate a problem that was building up. So we'll look forward to seeing you in part 2. Remember to be good to each other, stay safe, and remember you need to know what your plants need to grow.